Hello?
Hello, Dr. Larter.
Yes, that's right.
Hi,
This is Rob Larter here.
This is Becky Minzoni.
Okay, hello, Becky. How are you?
Good, good. How are you?
We're fine. So we're on the Nathaniel B here, just in the Amundsen Sea, and there are four of us here listening to the call. There's myself, there's my colleague Becky Minzoni, who's a marine geologist, and Anna Wahlin, who's a physical oceanographer and is responsible for the Hugin autonomous underwater vehicle.
Great,
And
great.
also
Well,
is our marine projects coordinator today.
Great. Well, thank you. Thank you very much again for making this happen. I'm sure the students are very, very excited. If you want to give some introduction about the work going there, and then we can go back to the questions.
Okay. Well, so this is a research cruise on the research vessel Icebreaker Nathaniel B. I guess that probably you've already researched all this. It's a multidisciplinary cruise. We've got 3 different research projects on here that are all part of something called the International Thwaites Glacier Collaboration, which has an overall aim to better understand changes that are occurring on the Thwaites Glacier in West Antarctica, and beyond that, how much and how fast that is going to contribute to sea level rise. So Thwaites Glacier was identified as the one in West Antarctica that's most vulnerable, and if significant change happens there, it could lead to a wider deglaciation of West Antarctica, which has a potential to contribute to about 12 feet to sea level rise overall. So the 3 projects, they go by the acronyms Tarzan, Thor, and GHC. We don't need to go through what those stand for. Tarzan is essentially a physical oceanography project, so Anna can talk about that, and particularly about the Hugin AUV that I saw there were a couple of questions about. Thor is marine geology and geophysics, so I can talk about the geophysics and Becky can talk about the marine geology. I haven't got anybody with me about the GHC project, which is an onshore geology. That was people going onto the islands to look at the history of sea level change from what they can find on the islands. So I think that's probably all I need to say for an intro. I don't want this to be a monologue. Can we ask Preves what the background of the classes? Have they taken classes in for example, geology and oceanography?
So this is the group. The students in this class tend to come from different backgrounds. This is kind of like an upper level undergraduate, but also we have some graduate students in the audience. Some of them are maybe dedicated in programs of environmental science, but not all of them. And they also have plans of doing various things. Some of them will be just high school teachers, but others who will start maybe graduate programs in environmental science.
Okay, thank you for that. So a broad background. So where do we want to start with the questions?
I'll ask maybe one of the questions. Ted, why don't you go ahead and start?
Hi, I'm Ted Wentz, environmental studies major here at Cleveland State.
Hi.
One of the first questions I have is, after the March 6th mission completed by the Hugin autonomous submarine, are you able to share some results that were obtained during the seabed mapping under and around the glacier?
Do you want to think about that?
Yes, that's me. Hello, this is Anna. I'm sorry about the accent. I hope you can understand me anyway. I'm from Sweden. So we got some interesting data. We are still analyzing the results, but we did get data of the ocean water underneath the glacier, and we did record some of the marks of previous glaciers moving over that area. So we hope with using this data, we hope to be able to say something about where the ocean comes from that we saw underneath there and how fast this ice sheet has retreated in the past. Was that
still
answer?
Sorry.
How much did you catch? Sorry.
Yeah, I was just, are you still analyzing that data that you obtained?
We're still analyzing, yeah.
Yes, we are still analyzing, yes. We have to compare different instruments that we have used, both on the Hugin and on the ships and on other vehicles like gliders.
Okay.
So it takes some time. Afraid it takes a while. We need the summer to analyze fully.
Absolutely.
Yeah, I think this is going to be a common theme that I'm afraid we don't have a lot of instant results. A lot of things, data needs to be analyzed. It needs to be calibrated. A lot of things, particularly with the water samples and the sediment samples, they need to go to the laboratories and be analyzed. And then it will be certainly some months before we can really put everything together. So a research cruise it's like a data collection factory, and then things come in much faster than you can deal with them. All we can do is record the data and put the samples away, and then we have to go back and look at it more carefully.
Yeah, feel free to continue, and then
thank you.
anybody else would.
I do have another question. Is there any evidence on the seafloor where the ice shelf used to reside that can assist in projecting the fate of Thwaites Glacier?
Well, yes. I mean, we can see evidence of where, particularly, this is something that you see all around Antarctica on the continental shelves. You can see the marks that were made by the glaciers and the ice sheet when it was far more extensive, and we can see the areas where the more extensive fast-flowing glaciers flowed, the areas where ice was slower moving and maybe frozen to the bed, and then we can see stages in the retreat. And it's quite well established now that you can see different kinds of marks that represent different speeds of retreat. What we won't know until we've done some radiometric dating on the sediment core samples is we won't be able to put a time frame on that. But yeah, we can see certainly in the new data we've collected from the ship and the very high resolution data that's been collected from the Hugin, we can see marks that have been made on the seafloor by different kinds of ice flow.
And what I should add is that the way that this will help in projecting the future of Thwaites Glacier is because looking at these seafloor features that give us evidence of when Thwaites Glacier was advanced over the ocean floor and then when it retreats, left these marks in the ocean floor. Once we date those, we can get an idea of rates of retreat, how fast that happened in the past, and whether that was associated with different conditions, either in the ocean or in the atmosphere, during warm periods or during cooling periods, or during periods where we had warm ocean water coming into this area, into this basin. So what our goal is to help, in projecting the future of Thwaites Glacier is basically to understand the past, what was normal, what were the triggers, and help feed that information to modelers that can better build these predictive scenarios for the future of Thwaites Glacier.
Great. Well, thank you for that. Something related to this, and this is a general question: is the Thwaites Glacier already entered? Did it enter already a phase of unstoppable decay?
I don't think we can answer that question at the moment. I think that answering that question is an overall aim of the International Thwaites Glacier collaboration. There are, within the collaboration, there are 8 funded projects. The ones here are just 3 of them. And this cruise is really the first major phase of scientific data collection. So as Becky said, a lot of the information we've collected really it needs to be fed into numerical models. So I think ultimately the big predictions of how fast it's going to contribute to sea level, and whether it's unstoppable collapse. Those answers will come out of the models once they've considered all the information absorbed all the information projects like ours can provide.
Megan, why don't you go, Megan? Yeah.
All right. Hi, I'm Megan Santiago. I'm an education major here at Cleveland State. My question is, did any of you encounter any setbacks while collecting your data or conducting your experiments?
Yes.
Yes.
I think we all experience setbacks, and much of the work here is to deal with the setbacks and make sure we get good results, even though they're not as we planned.
Yeah, I think it's a sort of running joke on the ship that in most Antarctic cruises that you make a plan every day, and if you're lucky, it lasts till lunchtime because things are always changing. The weather's always changing, the ice conditions are changing, bits of equipment break down and need fixing or recalibrating. So there's always things coming at you from all directions, throwing you away from your plan.
Yeah, that's been actually one of the cool parts of our cruise in a way, to give a little bit of a silver lining here. So we have a lot of students here with us, and people that are new to the science, at least to the field aspect of it. And they're having to watch us make these decisions on the fly when, a wrench gets thrown into our plans. For example, we had some bad weather days and we had to come up with backup sites to explore. We had sea ice come in and, just couldn't do all the work that we had planned. And, they were having to learn how to adapt just like us. So there's a lot of students just like yourselves that get to experience that. And it's actually part of the frustration and the joy of doing field work in these extreme and remote environments. You just have to be really good at being flexible and learning how to adapt to change that is constantly happening out here.
All right, thank you.
All right. Go ahead. Yeah.
Hi, this is Vincenzo Marinucci. I'm a physics education major at Cleveland State. Kind of off script from what I initially said, but you guys said this was like the first part of the studies on this glacier. Are you guys going to be, like you in particular, any of you going to be doing further studies, further expeditions?
Yes, we all are, yes. So Becky and myself, we have a further research cruise on this ship, on the Nathaniel B. exactly the same time next year, in fact. So we will be doing that. That will be the end of our field work, I think, and then we'll have about 3 years to really work through all the data and all the samples. And I think, Anna?
Yeah, and we have planned an expedition for us and Hugin on the Korean icebreaker next year, and then on the British icebreaker in year 3. So we will have 3 seasons in 3 consecutive years now.
Okay.
Okay, thank you.
Good. Go ahead.
Hi, I'm Dylan Anari. I'm a biology graduate. I was one of the questions I was asking is, in like the last couple of years, has there been any new technological improvements or new methods discovered that really let you guys like do these experiments that weren't potentially possible before?
Oh yeah, I mean there's been a lot of technological advances, and I think Anna is probably the one who should be answering this.
Yeah, it's not really a new technological advance with autonomous underwater vehicles, but they are quite new to science, I would say. They are used in other fields.
Yeah, I mean, a major advance from the marine geology side, I think, is with the radiocarbon dating, that over the last few years, the the quantities of material you need in of carbonate material, which is usually what we date. The quantity you need to get a radiocarbon date has gone down to the order of magnitude or more. So and that's particularly important for Antarctic research, where we don't have much of this material in the sediments. It's always been very difficult to get enough to get radiocarbon ages, and now that's becoming a lot more feasible in a wider range of sediments, which makes a big difference to the kind of work we're doing.
Yeah, so that's the carbon dating that we do. That's how we get at this question of rates of retreat for the past, and the different triggers potentially for those past retreats to help us understand the current stability of Thwaites Glacier. And so that's all looking for shell material is constantly what we're doing after we take these seafloor sediment samples. So that's been a great technological advance. It's just that analytical ability to use less material because there's just so little of it here. The other thing too that Rob knows a lot about is mapping of the seafloor. So we've actually advanced quite a bit in the resolution at which we can see these different features that are left behind by the glaciers at the seafloor. So instead of looking at pixels on the order of 5 meters, now we're looking at 10 meters. And with the Hugin, which Anna's team has deployed now, even to underneath an ice shelf, which is amazing. We can look at even finer scale features on, the 10 centimeter scale. So we're able to understand the history of Thwaites Glacier at levels that we maybe hadn't even considered were possible 10 years ago. So there's been a lot of technological advances that have advanced our science in ways that we have been very happily surprised with.
Great, feel free to jump in. Lisa, go ahead. Lisa, Jessica, go ahead. And Ted, you can always
Hi,
come
my name
in.
is Lisa Parrish Thompson. I'm a senior biology major with a minor in environmental science. And I'm wondering, as of now, I understand you're still analyzing data, but what is the most surprising, interesting, or shocking thing that you've learned about the Thwaites Glacier from what you've collected so far?
Yeah, I think we were all very surprised when we first had a close look at it because, well, first of all, you have to understand that no ship has really been into the area where right to the front of Thwaites where we were working, and it just visually it was very different from a typical ice shelf elsewhere with a lot of rift zones coming down to the front, and the surface of the ice shelf was very undulating rather than being like a flat slab. And it really wasn't as thick at the front as we might have expected, knowing how thick the ice is just a few tens of kilometers away at the grounding line. So, and then while we were there was a sort of carving event where a large part of the ice front sort of broke away and came out to actually flooded the area where we had been working with icebergs and brash ice. So that was over a day or so. That was a very dramatic event when you look at it in satellite images now.
Well, thank you.
Ted, you want to go
We're all
in?
really
Jessica. Probably I'll give some time for this to see what questions they will ask. Let me ask you one question that had to do with the modeling, of ice sheets. Apparently from all the reading that the students did and all that, it seems to be difficult. I'm not sure, and the students are asking, is it really the physics of decay, or is it the interaction with the dynamic changes in the waters that makes the modeling of ice sheets changes very difficult, or both?
It's the things the modelers struggle with. First of all, not having the best possible data, which is one of the things we're here to try and help them with. Particularly the one thing they always ask about is better data on the bed of the ice sheet. So we will get data on the bed that it's retreated from, and then people doing radio echo work on shore will get a better data on the shape of the bed. But a very important thing to know about is the characteristics of the bed that the ice sheet is, the ice stream, the glacier is running on. Whether it's sediments or whether it's hard rock, whether there's a large amount of water around or not. Because fast-flowing glaciers, they move largely by sliding at the base, and it's knowing what's controlling the sliding that makes it difficult. One of the things that makes it difficult to model. Another thing is that the amount of melting that happens beneath an ice shelf, it depends a lot on some very small-scale processes at the interface between the ice and the water, and this is something that remains to be precisely understood. This is a field of a lot of research.
And if I can add to another thing, I think is that the fact that we are overarching two subjects, it's glaciology and oceanography, and we are trained in different schools. So there's a special challenge there when we have to actually work together in order to really understand it.
Hi, I'm Jessica. I am a biology major seeking to be a 7 through 12 educator. I was reading articles and I saw that you use the process of interferometry. Okay, there we go. And I was just kind of wondering how that process actually works and what kind of technologies that involved.
Okay, I don't think it's any of our fields, but as far as I understand it, what people do is take two scenes of satellite data that cover exactly the same area taken at different times, and then you can look at any very subtle differences in elevation by showing the difference of the phase of the arrival of the radar signal. So where this the way this is usually shown is with different colors across the spectrum, so that as you go from no change to a bigger change to one full wavelength, you go through the spectrum, and then where there's a lot of change, you see these spectral bands where you can see that you're cycling through different wavelengths. So it's a way of bringing out the differences between two satellite scenes, which is very sensitive, for example, to where the grounding line is, because then you can see the tidal motion of the floating ice when you look at the two scenes taken at different stages of the tide.
Hi, this is Ted again. My other question is, does the current pace of environmental pollution and ocean acidification reflect the changes you see, or are the predictive models not holding true?
Well, so that's something that's hard to observe in Antarctica directly. But I mean, there are indirect ways of studying that here. Certainly, greenhouse gases like carbon dioxide are increasing the amount of the intensity of the greenhouse effect, and so we think that is part of the reason why the glaciers in the Antarctic Peninsula, for example, are rapidly warming and receding from the ice fronts that we observed just 10, 20 years ago. So there's been a lot of changes in the peninsula that we think are directly related to that we can observe here. The things like ocean acidification, those are more directly observable at places where we have reefs. And so, for example, in Belize and in the Bahamas and in the Great Barrier Reef, over the last even 2 years, there's been these really strong coral bleaching events where the ocean water is too acidic and actually causes the polyps of the corals to die, and so causes the corals to turn completely white. That's why it's called bleaching. And then, even over just the course of a couple of years, that entire area that was bleached very quickly becomes this, kind of dead and lifeless scene where you have these corals that are now being encrusted upon by, algae and things like that. So ocean acidification, we can observe and see quite directly the effects of increased greenhouse gas concentrations in the atmosphere that are, interacting with the ocean and causing the ocean to become more acidic. But that's something we can't directly observe here in the Antarctic. In the Antarctic, what we typically see is increasing temperatures, especially in the more northerly parts of Antarctica, like the Antarctic Peninsula, that we think are causing rapid melting of the glaciers in that region. Does that help answer the question? Your question?
Yeah, thank you. Yeah, so basically, I mean, the glaciers, so they're kind of being attacked from two sides then. You have geothermal heating attacking from underneath, and then the increased temperature on the surface then?
Well, so it kind of depends upon the region where you're looking. There's certain areas where, yes, geothermal flux is more important, especially areas where you might have more recent volcanism, for example. The Antarctic Peninsula is the area where we know that there's a very rapid warming going on. Where we are farther south in the Amundsen Sea near Thwaites Glacier, there isn't as rapid of an atmospheric warming. We're not really observing that here. What we are observing is there's a rapid ocean change. I'm gonna let I'll step in here. We have too little data. We have or not actually observing any warming in the ocean here in the Amundsen Sea. Actually,
but we do know that there's a lot of melting going on at the base of the ice shelves, which is driven. There is warm water here. Yeah. What Anna's saying is it's not getting even warmer. The thing is, the rate of retreat that we're seeing of the Thwaites Glacier and the neighbouring Pine Island Glacier, they're rates that can't have been going on for very long because, otherwise it would have retreated all the 500 kilometres from the shelf edge in the last few hundred years. And we know that it was already back to near the position it was when it was first observed. It was already near that position 10,000 years ago. So the rates of retreat and thinning that we're seeing now are unusual. And also we have evidence now from sediment cores that the warm water we see against the glaciers today was not in that position in the early 20th century. There was a change somewhere in the middle of the 20th century where it's the circulation of the warm water rather than the temperature of it. The warm water has always been there, it's just been out in the deep ocean. What's happening these days is that the warm water is getting to the ice margin and affecting the ice sheet.
So to further clarify what Rob was saying and what Anna was saying is that there's this ocean mass that travels around the Antarctic continent that's relatively warmer, and so the position of that proximity of these glaciers where they're draining to sea is what is changing right now. So
we think that because it's warm water here and the glacier is still here, so we don't actually have. We have not observed that this ocean water mass is. But you have to understand that we are in severe lack of data here. The longest time series from the Amundsen Sea is only about 7 years, and that one has a gap in the middle. So we really want more data and more long time series.
Yeah, and even that's continuous data series that Anna's talking about, but even proper observations, what we would call modern scientific observations of oceanography and good quality satellite imagery, these only go back about 25 years. Then that's kind of sporadic observations. So Anna said 7 years, that's ocean mooring, but continuous. So yeah, as the picture is, we need a much longer time series of observations really. Glaciers, a lot of the responses of glaciers and ice sheets are on much longer timescales than that.
And so that's where the international collaboration has been so productive, actually, is because, we're combining these continuous observations, of the ocean masses themselves with our deeper time observations that we can reconstruct. We can actually extend these instrumental records through looking at proxies in sediment cores. So the sediment cores, what we're measuring are these indirect variables that should tell us about ocean temperature, ocean salinity, and even, ecology, the organisms that are living in these basins over time, and how that influenced the glacier. So that's why this collaboration, coming at it from so many different perspectives, has been so productive for us.
Thank you.
Hi, it's Lisa again. I wanted to ask you, in such a tumultuous climate, both politically and physically, what words of hope or encouragement can you offer students about to begin careers in environmental science?
I have one. Can we give one each? My advice is stop doing math. You will need it. Yeah.
I guess my advice is to think about the impacts of what you do, whether you go into science or whether you go into science education, which it sounds like a lot of you are planning to do. I think the number one most important thing to think about at this stage as a student is to think about the impact of your work, whether you're educating, whether you're trying to push the boundaries of what we know through doing, science research. Think about the impact of what you're doing. For myself, I come from an area that has had very severe impacts due to climate change, due to extreme weather events. So I come from New Orleans. I grew up below sea level, literally, and so I have this strong motivation to understand the current changes in our global climate system, so that we can better build policy for regions where people live, and especially vulnerable communities like developing countries and like the people that, have to live in flood zones because they can't afford to live in the, more secure areas of their communities. So that's my biggest advice. Find your motivation, especially in environmental science. It's a very direct one, and let that drive you on your path to your future career.
Yeah, I'd say that there is a real buzz from doing scientific research, finding out new things, and then telling the world about them. And particularly, I think that this kind of study, there is a real particular buzz of this because, there is some societal relevance and policy relevance to what you're finding out. So, it's definitely, there's some obstacles, and it's difficult to get established in a career. You've got to get funding and stuff, but if you're determined, it's really worth it, because I think, for example, we're all really buzzing with the experience we've had here.
Thank you.
Okay, any more questions? I guess this was maybe a good question to finish this lively interaction with the student. It offers some advice and some hope, for the future. Well, I think the only one of the students, actually, just to give who could not attend, with us, she sent a question earlier, and I would like to have it part of this conversation before we close. And she was asking about the cavity under the glacier, under the Thwaites Glacier. Some say it is the size of Manhattan. The question was about the rate of increase of the cavity, and if any of the current studies would be would inform any of our actions in terms of policy to either stop it or slow it down?
I know what this is referring to. There was a lot of newspaper coverage of a paper that came out. I think it was just about when we started this cruise, in fact.
Yes.
So the cavity that was discussed, it's actually quite a local area beneath the ice shelf near the grounding line of Thwaites, and it's a difference over a period of about a year or 2 years that this amazing rate of cavity formation happened. And it's also the area where we saw, downstream of that, we saw this breakout of melange or icebergs and sea ice. It's not the whole of the Thwaites grounding zone that's melting at that rate, but it is quite. Actual headline rate is just amazing there. I'm not sure what else you wanted me to say about it.
Thank you. On that note, I would like to, on behalf of the students here at Cleveland State University, I would like to thank you, Rob, Becky, and Anna, and all others, for really taking the time on your busy schedule. And we know it's not always easy, but we really appreciate the students, and I really appreciate your time and effort to make this happen. This is really a very, very good experience for our students, and only time will tell what impact this particular interaction will have on their careers. Thank you again.
Well, thank you, and well done to you for taking the initiative to set this up. And I guess I'd like to say to all the students, have a great spring break now.
Yeah, woo. Have a good
Thank you. All right, take care.
Okay.
Take care.
Thank you.
Bye.
Bye.